Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is changing bases, and this is really a lecture that's a segue from our understanding of matrices of linear transformations to eigenvalues and eigenvectors. So the question that we want to ask is that if you have a vector space, why would you ever want to look at different kinds of bases and not just stick to the one basis that you found the first time around and you already liked? So we'll get started by giving you a motivating problem, a problem that we will solve as we go along in this lecture. So we have this 3x3 matrix. I mean, think that if you might have a 100 by 100 matrix with lots of data, then you might want to do this. But for our purposes, proof of concept, we're going to stick with this matrix A. And let's say that you wanted to find A to the 100. So whatever your day job was required you to find A to the 100. And this can come often. There are many times when you want to raise a matrix to a power. How would you do that? Now, you could just sort of sit there and keep multiplying it, or have a computer multiply it to 100 is not that big for a 3x3 matrix. But if matrix was much larger, then this might not be quite the idea to actually multiply it out. So we want an alternate method. But before we do that, we remember that whenever we see a matrix, you can think of it in two different ways. You can think of it as a matrix, a collection of numbers and organized in a certain way. And because of that, you can think of things like the null space and the row space and column space. Or you can think of that matrix as actually a linear transformation. A linear transformation, in this case, that goes from R3 to R3 and is defined by LA of x is A times x. So you take something in R3, which is a 3-tuple, an element of R3 is a column vector with 3 elements, and you take A times that, and you get another column vector. And you can think of that as a function that goes from R3 to R3. And it's not just a function, it's a linear transformation from R3 to R3. It's a linear operator. In this case, for example, if you do that, and if you take an arbitrary element of R3, A, B, C, and multiply A by A, B, C, this is what you get. And so you can actually write down what that linear transformation is. A, B, C goes to this, this other triple. Each one of those is one real number. Each one of these entries, this is one real number, that's another one, and that's a third one. And this is a linear transformation. Now, why, if you think about linear transformations, what is that question about A to the 100? Well, if you take LA squared, the square of this linear operator, which what that means is that you compose that linear transformation with itself. And you can do that with linear operators that go from the same vector space to themselves. You can compose them with themselves. Well, what does happen? You get another function from R3 to R3. And what does it do to a typical element of R3? What is LA2 of x? Well, LA2 of x is going to be equal to it's going to be equal to LA of x. That's what it means to compose LA with itself. Now, LA of x itself is A times x, and LA of that is A times that. And so what we have is LA of AX, and then that's A times AX, and that's the same as A squared x. So LA2, what it does is that it sends x to A squared x. So what does LA3, when you compose LA with itself 3 times, does to x? It sends it to A cubed x. So the thing that we really want to find is LA to 100. And in fact, if you think of it that way, you might think of other uses for this this process. So often you might have a linear operator doing something on a vector space, and you want to keep repeating it. You might have a dynamical system, for example, where you want to see what happens when the certain operation is repeated over and over again. And you want to see after 100 times where you'll end up. So these are the same question. What's A to the 100? What's LA to the 100? LA to the 100, again, is the composition of LA with itself 100 times. Okay, now to do this, let's remind ourselves of things that we have talked about in previous videos. One of them is, what is a matrix of a linear transformation? So if you have two vector spaces, finite dimensional, let's say dimension of the first one is n, and dimension of the second one is m, then, and if you have a linear transformation from V to W, then you pick a basis, an ordered basis for V for the domain, V1 through Vn. There's n elements because the dimension of V is n. And you pick an ordered basis for W. And that will have m elements, but I don't need to know the names of those elements. And so I've not written down what elements of B are. And then the matrix of T with respect to S and B, S is the matrix of the domain, B of the codomain, is defined in this way. So first of all, the notation we use is the matrix of T with respect to S and B. We read it as S and B, matrix of T with respect to S and B, even though we write the matrix of T subscript B comma S. And then this is the matrix. And what is this? Well, I've told you what the columns of the matrix are. So the first column, to find it, you take the first element of the basis for the domain, you send it over using T, you find T of V, and then you take T of V, which is an element of W, and write it in terms of B. You find its coordinate vector with respect to B, which will be a bunch of scalars that you need to write T of V1 in terms of elements of B. Those scalars give you a column vector in Rm, and that will be your first column. For the second column, you go to V2, send that over, find T of V2, find the coordinate of T of V2 with respect to B, and that will be your second column, and so on. Again, we have talked about this in detail in previous videos. And what this matrix does is that it does the job of the linear transformation for you. So if you want to know what you have some vector V in V, and you want to send it over, and you want to see what it does, what T does to it, well, you take V and you first write its coordinates with respect to S. The coordinate of V with respect to S, again, is a column vector, and you multiply it by this matrix. So you have this matrix of T with respect to S and B times the coordinates of V with respect to S. And what you will get is not T of V quite, but it's the coordinates of T of V with respect to B, from which you can figure out what T of V is. So every linear transformation, you get a matrix for it as such. Now, one particular kind of linear transformation, which the linear transformation itself is trivial, gives us this thing called change of bases matrices, which is the subject of this lecture. So change of bases matrix, actually, we have talked about in detail in another video, so I'm going to remind you, but then we're going to use it to solve our motivating problem. So if we take the identity transformation from V to V, so that's a linear operator. This is not the only linear operator there is. There's plenty of other ones. This is a trivial one. It's one that sends V to V. This is this particular linear operator. And but we pick a basis S for V and another basis B for V as well, one for the domain, one for the codomain, and we find the matrix of this linear transformation with respect to S and B, as I said in the previous slide. That matrix is called the change of basis matrix from S to B. If you pick the two bases to be the same, this would have been the identity matrix and not that much interest. But when you choose two different bases for a vector space, then you get this change of basis matrix. And the things you need to know about change of basis matrix is the following. First of all, if S and B are bases for n-dimensional vector space V, actually they have to be ordered bases. The order matters as well. Then this notation, the matrix of identity with respect to S and B is the change of basis matrix from S to B. And if you know what the elements of S are, and if you go back to the previous slide and apply it to this particular linear operator, you will get that this change of basis matrix is given actually in this way, in a way that you don't have to even know about linear transformations to talk about it. All you do is you take elements of S, the old basis, and you write them in terms of the new basis. So V1 in terms of B, V2 in terms of B, those are the coordinates of V1 and V2 with respect to B, and those are column vectors, and that gives you the change of basis matrix. The second thing you need to know is that what does this change of basis matrix do, and what it does, according again to what matrices for all linear transformations do, is that if you take the coordinate of V with respect to S, you will get and multiply it by this change of basis matrix from S to B, then you get the coordinate matrix of V with respect to B. So the purpose of finding this change of basis matrices is that it changes coordinates for you. If you have the coordinates of vectors with respect to S, maybe S is your old basis, the standard basis, and you want them in terms of B, you just multiply them by this matrix and you get the new coordinates. Now, to do that, you would have to find the coordinates of V1, V2, Vn, the old basis, in terms of the new basis B. But the third one tells you that if you wanted the change of basis matrix from S to B, it's also the inverse of the change of basis matrix from B to S. So first of all, these matrices are always invertible, but also going from one way and the other are going to be inverses of each other. That's important because often one of these is easy to write. So to find the change of basis matrix from B to S, from new to old, often is easier than from S to B. And so you find one and then you just find the inverse matrix and you get the other. Finally, let me remind you what similar matrices are. So you have a linear transformation from V to V, and linear operator that takes elements of V and gives you elements of V, and you have certain basis for this linear for this vector space V S, and so with respect to this basis, this linear transformation will have a matrix, but you might also think of another set of bases another basis for the vector space V, and L with respect to those bases will have a different matrix. And so so the matrix of L with respect to S, so this is the matrix of L with respect to S and S. For shorthand, we don't write S comma S when the basis for the domain and codomain are the same. We just write the matrix of L with respect to S. M is the matrix of L with respect to this basis, and N is the matrix of L with respect to the other basis. Now, these are both matrices of the same linear transformation, but they may look very different because we use different bases to find them. So now, how are these two matrices related? Well, we can relate the top part of the diagram to the bottom by the identity transformation. So you go from V to V by doing nothing. Identity again sends every element to itself. And you go up here from V to V again with identity doing nothing. Now, if you can start from the top left and apply L and go to the top right, or you can come down, do nothing, apply L, and then do nothing again. And both the times you're applying L, that's the only thing you're doing to an element of the vector space V, and you should get the same thing. So going across the top or coming around the roundabout way should give you the same answer. So in other words, so the composition of those three linear transformations is just going to be L. But this linear transformation, the identity linear transformation, also has a matrix, and its matrix is the change of basis matrix from B to S, which I'm calling P. And the other guy also has the change of basis matrix as its matrix, the change of basis matrix from S to B. And this one is the inverse of the other one. So I don't need a new name for it. I can just call it P inverse. So the first thing that I repeat what I said before is that going across the top, that's L, is the same as if you compose these three linear transformations. At the level of linear transformations, this is pretty trivial. It says if you don't do anything, then if you do L and then don't do anything again, that's the same as doing L, which is obvious. But when you compose linear transformations, what happens to their matrices? Their matrices get multiplied. So that tells us that N, the matrix that does the job of going across the top, is the same as P inverse MP. Now, P inverse comes first and P comes last because P is actually the first thing we apply. And when we are using matrices, we take matrices and multiply them by column vectors. We put the column vector at the extreme right, and P is the first guy that gets multiplied by that. So we need to do P first, and the first one that gets multiplied is going to be on the right. And then we apply M to the result, and then P inverse. And so N is going to be P inverse MP. And you can write this in the notation that at first seems quite cumbersome, but if you get used to it, is actually sort of helpful, that the matrix of L with respect to B is the matrix of identity with respect to S and B times the matrix of L with respect to S, and then times the matrix of identity with respect to B and S. And remember, these two are change of bases matrices. Okay, what does this have to do with our problem? So let's go back to our problem, but note that the vocabulary we have been using is that these two matrices are similar matrices, two matrices of the same linear operator. If you have a linear transformation from a vector space to itself, and you find two different bases, use different bases, one time S for the domain and the codomain, and one time B for domain and the codomain, and find the matrix of that linear transformation with respect to one of those bases and then with the other, the two matrices you get might look very different from each other, but they are similar to each other. That's the word we use. Similar is a technical word. Okay, so now let's go back to the original problem and let's see what did that have to do with finding a to the 100. Well, here's the matrix A, and the first thing I'm going to do is I'm going to say, well, there's a linear transformation associated with that, and we talked about this before, goes from R3 to R3. LA of ABC is the same as A times ABC, and if you multiply this matrix A with the column vector ABC, you get this. So this is what the linear transformation is. Now, this is the linear transformation, LA is the linear transformation corresponding to A, and what happens if I, well, if you take the standard basis for R3, and if you say now, we started with A, we found the linear transformation associated with A, but now I'm asking you, well, what happens if you find the matrix of this linear transformation with respect to the standard basis? You will get A. And the reason is that if you start with one of these vectors S and use LA and send them over, that's the same as taking A and multiplying it with 1, 0, 0, and that gives you the first column of A. And then if you multiply A by 0, 1, 0, you get the second column. If you multiply A by 0, 0, 1, you get the third column. And so the matrix that you get is going to be A. So we have a linear, you can think of it as we have a linear operator, and one of the matrices associated with it, the matrix associated with it in terms of the standard basis is A. This is sort of a weird way of thinking about it because we had A to begin with. All I'm just saying is that you can put the linear operator center stage and say, well, we have this linear operator and its matrix with respect to S is A. And ignoring the fact that we actually got that linear operator from that matrix. Why would I do that? Well, now I'm going to come up with a new basis. So S was the old basis, the standard basis, and B is going to be a new basis. And for now, I've just pulled that out of a hat. It doesn't look like a nice basis. And this fact, this was the point of this lecture. Why would you ever use such a basis, such an ugly basis, instead of 1, 0, 0, 0, 1, 0, 0, 0, 1, which would be sort of a really nice basis, the one we're used to. If you've done multivariable calculus, that's what we would call I, J, and K, and you write everything in terms of them. Why would you use 2, 2, 5, 2, minus 1, 2, and minus 1, 1, 2 as the basis for R3? Why would you do that? Well, for whatever reason, if you do that and you find the matrix of linear transformation LA with respect to B, you will get another matrix, and that matrix will be similar to A. And hopefully the word similar is not misleading, and that matrix will have actually something to do with the matrix A, and maybe will help us in finding A to the 100. So let's actually find that matrix and see what that might be. So again, here's our setup. We have that ugly looking matrix A, and LA is the linear transformation from R3 to R3, but we want to find its matrix with respect to B, which is this new basis. So what do we do? Well, so we have to take every element of the basis and send them over. So so we start with the first one. 225 is the first element of the basis. We find LA of 225, but to find LA of 225, you just take A and multiply it by 225. And if you do that, you get 8820. Well, is that going to be the first column of my new matrix? No. What you have to do now is to have to write this in terms of B. After you write this in terms of B, then that's going to be your first column of your matrix. So writing this in terms of B means write the coordinate vector of this with respect to B, and that means figure out how many of the first element, how many of the second element, how many of the third element you need to make 8820. B is a basis, so you will always succeed. So what we're looking for is the coordinate of LA of 225 with respect to B, and that's the same as the coordinate of 8820 with respect to B, but 8820 is actually just 4 times the first element, 4 times 225. So all we need is 4 of the first element, none of the second, and none of the third to get 8820. So the coordinate vector of 8820 is 400. That is going to be the first column of this new matrix. Now we repeat that for the second one. LA of 2, again, we multiply 2 minus 1 to A times 2 minus 1 minus 2. 2 minus 1 minus 2 is the second element in that ordered basis, and we get minus 848. What we need is take this guy and write it in terms of B. And again, we notice that all you have to do is multiply the second element in the basis by minus 4, and you don't need any of the first or the second to get minus 848. And so the coordinate of minus 848 with respect to B is 0, minus 4, 0. We do repeat this for the third one. The third element of the basis, minus 1, 1, 2, is sent to minus 7, 7, 14. And the coordinates of that is 0, 0, 7. This is just 7 times the third element. As a result, these are the columns of my new matrix. And so the matrix of LA with respect to B and B is this diagonal matrix. A diagonal matrix is a matrix that has zeros everywhere other than possibly on the diagonal. And this is a much nicer matrix than A, and it's similar to A. So matrices A and D are similar. And so we're going to use that to our benefit in terms of finding A to the 100. So let's think about what we did just one more time before we actually find A to the 100. So we had this matrix A, we had this basis B, which you should be asking, where did that come from? I haven't told you. In the last slide, I will tell you what properties that basis has. And then when we talk about eigenvectors and eigenvalues, we'll find out how to find those kinds of bases. So we had this basis out of the hat, and then we found the matrix of LA with respect to B, and that was this nice diagonal matrix. And so we found this other matrix that was similar to A. And how did we do that? By going over to linear transformations, and instead of thinking of the matrix A, thinking of the linear transformation in LA, and then finding the matrix of that with respect to the different bases, and we found this diagonal matrix. And so what we really are doing is that we're saying that there's a linear transformation in the background, but what we can use either matrix A or matrix D to do its job. You can use the matrix A as long as you're sticking to the standard basis for R3, which is something you like. But you can use this much nicer matrix if you're using the basis B. And these two the diagrams, so A and D are 3 by 3 matrices. They're matrices of the same linear transformation, but with respect to different bases. And how are they connected? They're connected with a change of bases matrix. So P is the change of bases matrix from B to S, and P inverse is the change of basis matrix from S to B. And if you write that, then D is going to be the same as P inverse AP. P is the first one, the one mostly to the right, and then A, and then P inverse. And so P again is the change of basis matrix from the new to old. We usually think of S as the old basis and B as the new basis, and P is the change of basis matrix from new to old. And then D, this diagonal matrix, is just P inverse AP. This is just a recap of the previous slide. Okay, now finally, let's find A to the 100. What are we going to do? But let's remember what we have. We have D is P inverse AP, but I don't want D. I don't want anything about D. I want to know something about A. So I want to solve for A to find out what do I know about A. So to do that, I multiply on the left by P, and I get PD equals AP. Then I multiply by P inverse on the right, and I get that A is PDP inverse. And so that will allow me to find A 100. But let me remind you what P is. P is a change of basis matrix. B is this weird matrix, 2, 2, 5, 2 minus 1, 2, 1 minus 1, 2. And then P is the change of matrix basis matrix from B, this new basis, to the old one, S, which was the standard basis. But how do we find that? Well, what I have to do is I have to take these guys and write them in terms of standard bases, but they're already written in terms of standard basis. So this is the first column of the change of basis matrix, and the second element is also the second column, and the third one is the third column. There's nothing to be done. Because S happens to be the standard basis and the elements of the new basis are already written in terms of that, all I have to do is put them together to find P. And finding P inverse is just a matter of plugging this into a computer and telling me what the inverse is, or doing it by hand. It's not that bad. P inverse is this other 3 by 3 matrix. So now I know that A is PD P inverse, and I know what P and P inverse is, and D was that diagonal matrix. So now how am I going to find A100? Well, instead A100 means A times A times A times A times A 100 times, and each one of those A's is PDP inverse. So that means that I need to multiply PDP inverse by PDP inverse by PDP inverse 100 times. Okay, so what happens here? Now, matrix multiplication is associative, so I can't, it's not commutative, I can't move things around, past each other, but I can switch the place of parentheses. So this P inverse can get multiplied by that P, and that becomes identity, goes away. And then D and D multiply, and I get D squared. So I get PD squared P inverse. But that P inverse gets multiplied by the next P, gets away, and that D squared gets multiplied by D and gets D cubed. And so when you get rid of all the P inverse P's and collapse all those into identity, and identity just do anything, what you're left with is P D to the 100 P inverse. Okay, so actually I now know something about this. So do I know D100? Well, D was this diagonal matrix, 4 minus 4, 7 down the diagonal, and diagonal matrices are very easy to multiply by themselves. When you multiply this guy by itself, you just get 4 squared minus 4 squared and 7 squared. So when you find D to the 100, you will get 4 to the 100, 4 to the 100, and 7 to the 100. Minus 4 to the 100 is the same as 4 to the 100. Okay, and then finding A to the 100 then just becomes multiplying P, that matrix P, this matrix P, by D100 by P inverse. It's just two matrix multiplications. So I take P, D1 to the 100 and P inverse and multiply them. It's just two multiplications. It's not multiplying A by 100 was multiplying 100 A's together. This time you're just multiplying one product of matrices and then another one. And you can do that, and you get something very ugly in this case. But I should, and this is not an approximation. This is exactly what A to the 100 is, and so we were able to do that. Now, the only hole in the whole argument is that where did that matrix B come from? And so let's think about that. So we had this matrix A and matrix D, and these were similar to each other. And the key to that was that basis B. And the question we have is that what kind of a basis do we need so that the matrix of LA with respect to that is a diagonal matrix? How did we manage for D to become diagonal? Well, so as proof of concept, we'll focus on the second column. How did it become that the second column was 0 minus 4, 0, which is what we need for a diagonal matrix? Well, how did we get 0 minus 4, 0? Well, we had how we got that was that we had this basis, and for the second column of the matrix of our linear transformation, we have to take that second basis element, send it over, and then write it in terms of B again. So we're finding the matrix of LA with respect to B and B. So we take the second, for the second column of that, we take the second element of that basis, send it over, but then write it again in terms of the same basis and see what the coordinates are. For the first and the third column, we do similar, but with the other guys. And so we had to find LA of 2 minus 1 minus 2. And the point was that, well, you multiply A by that, and we got minus 848. But minus 848, the thing about that was that it was minus 4 times 2 minus 1 minus 2 times the same element that we sent over. We sent this basis over, but what we got is minus 4 times itself. The reason that's important is because when you get minus 4 times itself and then you want to find its coordinates, you know what the coordinates are. You don't need any of the first one. You don't need any of the last one. You need minus 4 of this middle one. And so because of that, we had 0 minus 4, 0 as our second column. And in fact, this was true of all of the basis elements, that for all elements in the basis V, what we had was that when we multiplied A by them, we got a multiple of themselves. Why did we multiply A by them? Well, because that's how you find LA of V. And we got lambda times V. And so when we wrote the coordinates of this with respect to B, we just got a whole bunch of zeros and just lambda for where V was. And if you think about it, the first one had a non-zero entry in the first entry and zeros everywhere else. The second one has a 0, a non-zero entry 0. The last one has 0, 0, and then an entry, and that's a diagonal matrix. Now, whenever you have this, when you have a non-zero vector V, such that, I mean, you won't want in your basis the 0 vector, so V had to be also non-zero. A times 0 also has this property, but that's no good. So whenever you have a non-zero vector V such that AV is lambda V for some scalar lambda, then V is called an eigenvector of A, and lambda is called an eigenvalue of A, an eigenvalue corresponding to the eigenvector V. And for us to get a diagonal basis, what we needed was a basis consisting of eigenvectors of A. So a matrix A walks through the door, pretty ugly. What you need to do is, and you can think of that as that's the matrix of the linear transformation in LA with respect to the standard basis. And what you want is a new basis, and you want that new basis to consist of all of the basis elements be eigenvectors of A. And if you can do that, then you get a diagonal matrix. Now, all of that is fodder for our future lectures on eigenvalues and eigenvectors, where we will go in and see which matrices have will have enough eigenvectors for us to be able to find a basis for R3 made up of eigenvectors. And how do we find eigenvectors? So all of that will become clear later. But if you can do that, then the diagonal entries, that 4, -4, and 7, those are going to be the eigenvalues of the matrix. And again, eigenvalues and eigenvectors are a pretty important topic. And the purpose of this lecture was to show you that if you want to do something like take A to the 100, and if you could, one way or the other, by hook or crook, find yourself a basis for Rn, n being the size of your matrix, if the matrix is n by n, made up of eigenvectors of A, then you can solve the problem. And I will see you in the following lectures, which will be about eigenvalues and eigenvectors.